All right. An amusement park ride has a radius of 4.5 meters, is going 11.7 meters at the top of the circle. What is the centripetal acceleration? What g-force do they? So there's two parts. So this, we'll do this part 1, and then I'll hit erase and do this part. Okay, so this is a standard find the acceleration. So find AC in, in g's, right? So this is just A is v squared over r. So 11.7 squared divided by 4.5. $30.42. Right, and then to turn meters per second squared into g's, you just go meters per second squared divided by 9.8, right? So I'm going to take that and go 30.42 divided by 9.8, and I get 3.1, roughly 3.1 g's. So that's what the ride is actually doing, right? That's its acceleration in meters per second squared. There it is in g's, right? And then at the top, and it's only asking for the top, right? It's 1g minus the ride, right? So it would be 1g minus 3.1. That would be negative 2.1. So that's inverted, right? You'd be like upside down, weighing 2.1 times as much as you normally do, right? Okay. All right. Now let's answer the second question, which is what is the minimum speed it could go for the top for people not to fall out? That's a different thing. So let's just figure that out, right? So here it is in the circle. Right at the top, you want the acceleration to be greater than or equal to 9.8. So we'll just set it equal to 9.8, right? So we'll go 9.8 is v squared divided by the radius, which is 4.5. Right, so I'm using the formula centripetal acceleration is v squared over r and just solving for v. So let's see, 4.5 times 9.8. Take the square root of that, and we've got 6.64 meters per second. Ta-da. So if they say, if the people are not going to fall out, or the water is going to stay in the bucket, or all this stuff, right? What you want to do is set the acceleration, make that guy 9.8, and on Earth anyway, right? And that will keep that's the minimum you could have, right? Because remember, at the top it'd be 1g minus 1g. You'd be weightless for a moment, but you wouldn't be negative. You wouldn't fall. That's kind of cool.